What if we can never reach another Earth? What if the universe is filled with Earth-like worlds, and the laws of physics make sure we never touch a single one of them? Not just in practice, in principle. A cosmos sprinkled with blue planets, shallow seas, and breathable skies, all forever out of reach. How would we live knowing that? How would we plan our future if every other habitable world is a painting behind unbreakable glass? We have grown up on a diet of science fiction where this problem is already solved. Warp drives slice through space. Hyperspace lanes stitch stars into neighborhoods. Interstellar empires rise and fall in the time between commercial breaks. In the hunt for alien life, we casually hop from system to system, as if changing trains. But while our stories move at the speed of imagination, our spacecraft move at the speed of engineering. Voyager 1, the most distant human object, is racing through space at about 17 kilometers per second. Impressive. Until we ask a simple question, how long would it take, at that speed, just to reach the nearest star? More than 70,000 years. That is one star. Proxima Centauri, barely over 4 light-years away, in a galaxy 100,000 light-years across. This means that even the nearby stars are not neighbors. They are continents away, separated by oceans of emptiness that our current technology can only crawl across. So, let's begin with the uncomfortable possibility. If reaching another Earth is effectively impossible, then our entire future as a species might be limited to this one fragile planet. Every war, every civilization, every experiment in culture and technology, all confined to a thin film of rock and atmosphere around a single ordinary star. It should be noted that this is not just a philosophical worry. The more data we gather, the more it looks like the universe is not handing out second chances easily. From Kepler and TESS, we have learned that small rocky planets are common. Optimistically speaking, that sounds like good news. But when we point our best instruments at the most promising systems, the story becomes more complicated. New telescopes like the James Webb Space Telescope are not only revealing the atmospheres of distant worlds, they are quietly telling us something darker about how rare truly Earth-like, reachable planets might be. Take TRAPPIST-1, a compact system of 7 Earth-sized planets around a cool red dwarf, just 40 light-years away. On paper, it looked like a shortcut to a second Earth. In practice, JWST's measurements are forcing us to ask a harder question. What if even the best nearby candidates are either uninhabitable or forever out of our practical reach? So it's time to find out the truth. Are we standing at the dawn of a glorious interstellar age, or about to discover that we are, in a very real sense, cosmically stuck? For now, we will leave that question hanging. Why this question matters more than any space race. If we really might be cosmically stuck, then the next question is brutal. What does that mean for the long-term survival of our species? This is where the idea of another Earth stops being a cool science headline and turns into a civilizational mirror. Earth is not a permanent safe zone. Climate change is already reshaping our planet. Asteroid impacts have reset the clock on life before, and in about 5 billion years, the sun will swell into a red giant and erase the inner solar system. In the hunt for alien life, we often look outward, but these same discoveries force us to ask, do we have any realistic escape route at all? So, let's begin with the basic problem of scale. Our closest stellar neighbor, Proxima Centauri, is just over 4.2 light-years away. That sounds almost friendly, as if it sits just beyond Pluto. This means a bit more than 40 trillion kilometers of mostly empty space. And Proxima is only a single red dwarf, not a guaranteed provider of an Earth-like habitable world. It should be noted that even if a perfect twin of Earth orbited there, the distance alone would still be terrifying. We can make this concrete. Voyager 1, our most distant spacecraft, is racing through space at about 17 kilometers per second. That is fast enough to cross the continental United States in a few minutes. Yet at that speed, it would need over 70,000 years to reach Proxima Centauri. 70,000 years. That is longer than all of recorded human history, from the first cities and writing to the entire digital age, stacked end to end. So when we talk about reaching another Earth-like planet, we are not just talking about building a better rocket. We are talking about sustaining a mission, a crew, or even just functioning electronics, for timescales that swallow civilizations. Optimistically speaking, we might imagine world ships, frozen embryos, or digital minds crossing the void, but while those ideas are inspiring, the energy, shielding, and reliability they require push right up against the hardest limits of physics and engineering. And even if we somehow solved those, there is a deeper sting. Nearby, seemingly promising systems like TRAPPIST-1 tempt us with multiple rocky planets sitting in or near the Goldilocks zone. On paper, they look like a dream. 7 Earth-sized worlds around a single dim star, only about 40 light-years away. Yet distance, the brutal energy cost of near-light-speed travel, and the harsh radiation environment of interstellar space might still make them effectively unreachable for biological life. So it's time to find out the truth, because when we zoom in on TRAPPIST-1 itself, and on its most promising world, TRAPPIST-1e, we discover that the story of another Earth is far more complicated than the hopeful headlines suggest. And the real verdict from JWST might not be what we were expecting, from infinite possibilities to one tiny star system. If we cannot trust the headlines, what can we trust? In the hunt for alien life, we need at least one real example of a promising, concrete target. Not a vague, Earth-like world out there somewhere, but a specific star system we can point to and say, that one, let us test our hopes there. That is where TRAPPIST-1 enters the story. Instead of being lost in a sea of distant exoplanets, this single compact system stands out, only about 40 light-years away. Far beyond any spacecraft we can launch today, yes, but still practically next door on the scale of the Milky Way. When it was first revealed, it almost felt like the universe had handed us a carefully prepared laboratory. TRAPPIST-1 is an ultra-cool red dwarf star, only slightly larger than Jupiter in size, but far more massive, glowing dimly compared to the Sun. Around this small star, at least 7 rocky, Earth-sized planets trace out tight, resonant paths. 3 of them lie in what we call the Goldilocks zone, where, in principle, liquid water could exist on the surface. For a while, this system was the poster child for habitable worlds. Why did it capture so much attention? Part of it is the sheer number of planets. We know that Earth-like planets are fertile ground for life. After all, life arose here. So to find a planetary system that is seemingly full of Earth-sized worlds, all packed closer to their star than Mercury is to ours, felt almost too good to be true. Their orbits are so tight that a year can last just a few days, but while the orbits are small, the opportunity is huge. Because these planets pass in front of their star, from our point of view, every transit lets us study their atmospheres, or lack of them, in exquisite detail. This means TRAPPIST-1 is not just a curiosity, it is a test case, a place where we can ask, very directly, what a potentially life-friendly system actually looks like when our data finally become precise enough. It should be noted that this star is also unusually calm for a red dwarf, flaring far less than many of its cousins. Optimistically speaking, that made astronomers think fragile atmospheres might survive here, sheltered from the worst radiation. If any nearby system deserved the title of Best Chance for Another Earth, this was it. So let's begin our deep dive, because with the James Webb Space Telescope, we now have the power to peek into these worlds in a way we never could before, and the first results from this little star system may quietly rewrite what we expect from our interstellar future. JWST, the cosmic lie detector for another Earth. JWST is not just another telescope. It is, in a very real sense, our first lie detector for distant worlds that claim to be another Earth. In the hunt for alien life, we have never had an observatory like this. The James Webb Space Telescope is parked 1.5 million kilometers from Earth, shielded from the Sun, unfolding a mirror the size of a small house. But while Hubble saw mostly visible light, JWST is optimized for infrared, the faint heat glow of the universe. This means it can pick up the unique fingerprints of molecules in a planet's atmosphere from tens of trillions of kilometers away. How does that actually work? Imagine a TRAPPIST-1 planet sliding across the face of its red dwarf star. For a few hours, a thin ring of starlight has to pass through whatever atmosphere that planet has before it reaches us. JWST watches that transit and breaks the light into colors, like a prism. Certain colors get absorbed by specific gases. Water vapor leaves one pattern, carbon dioxide another, methane yet another. By measuring which colors are missing, we can decode which gases are present and even roughly how much. It should be noted that this is incredibly hard. The planets are small, the star is dim, and the signal is tiny, but while the challenge is huge, the payoff is bigger. For years, TRAPPIST-1 was a beautiful sketch, 7 Earth-sized worlds in the Goldilocks zone of possibilities. Now, JWST is the instrument that can finally deliver a verdict. Are these planets wrapped in thick, protective atmospheres, or stripped bare by radiation? Are they steamy greenhouses, frozen deserts, or something recognizably Earth-like? Here is the pattern interrupt. For a long time, many artists' impressions showed TRAPPIST-1e with blue oceans, clouds, perhaps even continents. With JWST, those paintings have to answer to data, and the early answers are sobering. Several of the inner planets already look effectively airless, their surfaces probably scorched and exposed. Others show no clear signs of the comforting mix of gases we associate with a truly habitable world. Optimistically speaking, this is still progress. We are no longer guessing from a distance, we are reading these worlds directly. JWST has already started multiple observing campaigns across the TRAPPIST-1 system, building up spectra transit by transit, year by year. So it's time to find out the truth. If the most promising nearby system, with 7 Earth-sized planets around a quiet red dwarf, turns out to be far less welcoming than we hoped, what does that say about our chances anywhere else in the galaxy? 2 futures: interstellar pioneers or cosmic prisoners? So that leaves us with a brutal question. In the very long run, do we actually leave home or not? Most of us grow up with a quiet assumption about the future. One day, humanity spreads from star to star, hopping between Earth-like planets in a kind of slow-motion migration through the galaxy. In the hunt for alien life, we picture ourselves as future neighbors, visiting other civilizations on worlds that feel almost familiar: oceans, clouds, blue skies. But while that is the optimistic picture, physics may have written a very different script. There is a second possibility, that we never become truly interstellar at all, that the laws of nature quietly lock us inside our own solar system, with other habitable worlds hanging in the distance like emergency exits we can see but never reach. So which future is real? On one side, we have the hopeful scenario: nearby, truly habitable planets, breakthrough propulsion that pushes ships to a decent fraction of light speed, manageable radiation, long-lived technology, and journeys measured in decades rather than tens of thousands of years. Optimistically speaking, a civilization with enough time and ingenuity might solve these engineering problems one by one. On the other side, the pessimistic scenario looks very different. Interstellar distances are so immense that even our fastest probes, like Voyager 1, would need more than 70,000 years just to reach the nearest star. This means that to cross the gap in a human lifetime, we would need staggering amounts of energy, almost absurdly efficient engines, and spacecraft that can shrug off radiation, micrometeoroids, and centuries of wear. It should be noted that none of that is forbidden by physics, but every step is brutally expensive. And all of that effort only makes sense if there is something worth reaching at the other end. That is where TRAPPIST-1 comes in. Because this system, with 7 rocky planets in a tight orbit around a quiet red dwarf, looked like the perfect test case. If any nearby star was going to host a second Earth, this was it. So the core question sharpens. Is another Earth a real destination that future ships might actually land on? Or is it a beautiful mirage? An Earth-like signal in our telescopes that turns out, on closer inspection, to be uninhabitable in practice? In this episode, we are going to walk through both sides. We will look at what the new JUST data from TRAPPIST-1 really show, planet by planet, and then we will run the numbers on interstellar travel itself to see how hard it would be to get there. And the twist is that the bad news does not start with rockets, or energy, or even with the vastness of interstellar space. It starts with the planets themselves, and with what JUST is quietly telling us about their atmospheres, who I am, what we'll cover, and where this is going. So if the trouble starts with the planets themselves, we should probably be clear about who is walking us through this mess. I'm Host Name, and this is Channel Name, a place where we take the wildest ideas in space science and run them through actual physics and real telescope data. In the hunt for alien life, we try very hard not to drift into wishful thinking. This means we are going to move step by step, not leap from cool exoplanet headline to pack your bags for TRAPPIST-1e. So let's begin by laying out the journey for this episode. We are going to build a staircase from stars to planets to spaceships to the long-term choices of a civilization. At each step, we will ask the same question. Does this make another Earth more reachable or less? First, we will stay in the comfort of telescopes and numbers. We will look at what systems like TRAPPIST-1 and the James Webb Space Telescope in particular are really telling us about Earth-like planets. Which orbits fall in the Goldilocks zone? Which worlds have any hope of a stable atmosphere? And where does TRAPPIST-1e sit once we strip away the hype and listen to the data? Then we will leave the observatory and step into the engine room. The second pillar is the brutal physics of interstellar travel itself. How far is 40 light-years compared to Proxima Centauri's 4.24? Why does Voyager 1, racing through the outer solar system at about 17 kilometers per second, still need tens of thousands of years to reach even the nearest star? It should be noted that this is not about pessimism. It is about the rocket equation, energy budgets, and what happens when you try to push real mass to a significant fraction of light speed. The third pillar is where it gets personal. If the universe offers us habitable planets that we may never touch, what does that mean for our future? We will explore alternative paths, robotic probes instead of starships, digital minds riding tiny spacecraft, world ships drifting slowly between stars, and the possibility that the most realistic Another Earth is a carefully managed version of this one. Along the way, we will keep zooming out to ask, what does this mean for us right now? Not just for astronauts centuries from today, but for a species that has to decide where to invest its effort, star hopping or building a deep, resilient civilization at home. And here's a small challenge for you as we go on. Pick a side in your head. Are we a species that will one day stand on an exoplanet in another system, or are we effectively stuck in our own cosmic neighborhood? Hold that answer. So it's time to find out the truth about whether the physics of the universe will let you keep it. The hidden rules of habitable worlds, so before we decide which future we belong to, we need to ask something even more basic. What exactly counts as another Earth in the first place? In the hunt for alien life, we often hear that a rocky planet in the Goldilocks zone is enough. The right distance from its star, not too hot, not too cold, and we are done. But while that picture sounds comforting, reality is much stricter. A truly Earth-like, habitable world needs a very delicate combination. The right type of star, the right orbit, a stable atmosphere, a protective magnetic field, and a calm enough environment to stay that way for billions of years. Miss just one ingredient, and the surface can swing from ocean paradise to sterile rock. This means we have to separate the problem into two layers. First, the astrophysics layer. Do nearby stars actually host planets that can keep liquid water and thick atmospheres over deep time? Only once we have believable targets does the second layer even matter, the engineering of travel. Can we cross the dark gaps between stars without breaking the laws of physics or our own civilization? It should be noted that if the first layer fails, the second becomes almost irrelevant. Reaching a world that only looks Earth-like on paper would be a very long, very expensive disappointment. Stars themselves set the stage. Their mass, temperature, and magnetic activity decide where the habitable zone falls and how harsh the radiation environment is. A hotter, more massive star puts its Goldilocks zone far out, but burns through its fuel quickly. A cooler star pulls the zone inward, but often bathes its planets in flares and high-energy particles. Around such a star, a planet might technically sit in the right orbit for liquid water, yet lose its atmosphere to constant stellar tantrums. So, let's begin with the obvious question we often skip. Before we talk about rockets, antimatter, or giant laser sails, are the stars near us even good hosts? Can their planets hold on to air, oceans, and magnetic shields for billions of years, the way Earth has under our relatively gentle sun? Or are most nearby systems only pretending to be inviting when viewed from far away? Optimistically speaking, the most common stars in the galaxy once looked perfect. Red dwarf stars are small, cool, and incredibly long-lived. Their habitable zones are close in, which makes Earth-sized planets easier to detect and, in principle, easier to reach. For a while, many hoped that these stars would be packed with quiet, stable, habitable worlds. At least that was the case, until we started looking more closely at real red dwarf systems, and one in particular, TRAPPIST-1 red dwarfs, abundant, long-lived, and surprisingly hostile so. What exactly are these stories pinned so many hopes on? Red dwarfs, or M-dwarfs, are the small workhorses of our galaxy. They are cooler, dimmer, and far less massive than the Sun, yet they completely dominate the stellar population. It should be noted that when we look at the Milky Way as a whole, red dwarfs vastly outnumber Sun-like stars. If you pick a random star in the sky, odds are it is a red dwarf. Being so cool and faint has a remarkable consequence. These stars burn their fuel with extreme efficiency, sipping rather than guzzling hydrogen. This means a typical red dwarf can shine not just for billions, but for trillions of years. In the hunt for alien life, that sounds almost perfect. A long-lived, steady star could in principle host a habitable planet for far longer than Earth will ever enjoy around our sun. But while that sounds like a cosmic paradise, the details are far less friendly. Because red dwarfs are so dim, their Goldilocks zone huddles very close to the star. To receive the same warmth Earth gets, an Earth-like planet must orbit at a fraction of Mercury's distance. The result is a system where any habitable world circles its star in just a few days. So, let's begin to see the problem. At those distances, tidal forces are immense, and the most likely outcome is tidal locking. On a tidally locked planet, one hemisphere faces the star forever, baked in eternal day, while the far side is trapped in endless night. Can such a world really be habitable? The day side risks becoming a scorched desert, the night side a frozen wasteland. Only a narrow ring of twilight around the terminator might hover near comfortable temperatures, and that would demand an atmosphere capable of efficiently moving heat around the planet. And even if such an atmosphere exists, it has to survive the star itself. Young red dwarfs are notoriously active. They unleash powerful magnetic storms, frequent flares, and blasts of high-energy radiation. Optimistically speaking, some planets might endure this phase, but many could see their atmospheres slowly stripped away, particle by particle, leaving bare, airless rocks in or near the Goldilocks zone. This is where TRAPPIST-1 becomes crucial. TRAPPIST-1 is an ultra-cool red dwarf, and it inherits all of these concerns. Its habitable zone is extremely close in. Its planets are almost certainly tidally locked, and although TRAPPIST-1 is unusually quiet for a red dwarf, it still flares, so it's time to find out the truth. Can any of its 7 Earth-sized worlds, especially TRAPPIST-1e, actually keep a life-friendly atmosphere in this harsh environment? To answer that, we have to look directly at the planets themselves, and this is where the James Webb Space Telescope finally steps in. TRAPPIST-1, the red dwarf that gave us hope so. Let's begin with the star that briefly made us believe the story might have a happy ending. TRAPPIST-1 is not a sun-like star at all. It is an ultra-cool red dwarf only about 9% the mass of the Sun and roughly the size of Jupiter. Imagine something barely larger than a gas giant planet, yet with enough mass to ignite nuclear fusion and shine for trillions of years. Around this tiny ember, astronomers found not 1 or 2 worlds, but 7 tightly packed terrestrial planets. Their orbits are astonishing. All 7 planets fit well inside the orbit of Mercury. A year there is measured in days, not months. But while the system is compact, it is also remarkably orderly, with the planets locked into a chain of orbital resonances. In the hunt for alien life, that kind of stability is very attractive. It suggests a system that could, at least in principle, remain calm for billions of years. Then came the first surprise. TRAPPIST-1 seemed quiet. For a red dwarf, that is unusual. Early observations showed that it flared much less often than many of its cousins, perhaps around 30 times less than a typical active red dwarf. This means fewer blasts of high-energy radiation stripping atmospheres away. It should be noted that this did not make TRAPPIST-1 gentle, only relatively restrained, but it was enough to raise hopes that some planets could keep a thick, protective atmosphere. And then the headlines arrived. 3 of the planets, TRAPPIST-1e, F, and G, fell squarely in the Goldilocks zone, where temperatures could allow liquid water on the surface. Their sizes and masses turned out to be very close to Earth's. Suddenly, we were looking at a single nearby system, just 40 light-years away, apparently holding multiple Earth-like planets in the habitable zone. How could that not capture our imagination? Optimistically speaking, early climate models painted an enticing picture. If these planets started with plenty of water, or if they possessed strong magnetic fields to shield them from the star, some simulations showed thick atmospheres surviving for billions of years. Oceans could form on the day side of a tidally locked planet, with winds and currents carrying heat into the eternal night. In those models at least, TRAPPIST-1e and its siblings were not just rocks. They were potential homes. But models are promises, data are verdicts. And when the James Webb Space Telescope finally turned its mirror toward TRAPPIST-1, the first precise measurements did something unsettling. They began to quietly dismantle that beautiful, optimistic picture. What did Webb actually see in those atmospheres? And which of these 7 worlds fell from grace first? How we found TRAPPIST-1's 7 worlds. To understand what Webb has taken away from TRAPPIST-1, we first have to ask, how did we even find these worlds in the first place? Because before there were atmospheres to disappoint us, there were just tiny, mysterious dips in starlight. In the hunt for alien life, most discoveries do not begin with majestic images. They begin with numbers. Back in 2010, a small team built a telescope with a very specific purpose: stare at faint, ultra-cool red dwarf stars and do almost nothing else. They called it TRAPPIST, and unlike the giant observatories you might imagine, it was a modest, ground-based instrument in Chile, with a twin later added in Morocco. So, let's begin with what these telescopes actually did. Night after night, they measured how bright each target star appeared, over and over, thousands of times. If a planet crossed in front of its star, even a world smaller than Earth, it would block a tiny fraction of the light. That is transit photometry. A shallow dip appears in the light curve, like a heartbeat on an electrocardiogram, and the depth of that dip tells us the planet's size, while the time between dips reveals its orbit. But while that sounds simple, the reality is far from it. In 2016, the team noticed not one, but several repeating dips from a faint red dwarf about 40 light-years away. Initial analysis suggested 3 planets. They announced TRAPPIST-1b, C, and D, roughly Earth-sized worlds, huddled close to a star only slightly larger than Jupiter. Pattern interrupt. Imagine being in that control room when the light curve refused to behave. The dips did not line up cleanly with just 3 planets. There were extra signals, overlapping, interfering, hinting at more worlds hiding in the data. Was it noise, instrument error, or an entire compact planetary system? It should be noted that this is where patience becomes a scientific weapon. The team brought in additional telescopes, including the Spitzer Space Telescope, to monitor TRAPPIST-1 continuously. With longer, uninterrupted stares, the puzzle snapped into focus. By 2017, the 3-planet system had transformed into 7 distinct Earth-sized planets, all packed inside an orbit smaller than Mercury's around our Sun. This means we were looking at a chain of rocky worlds, each tugging slightly on the others, producing tiny variations in the timing of their transits. From those variations, astronomers could estimate the planets' masses and confirm they were indeed dense, rocky bodies, not puffy gas dwarfs. Optimistically speaking, it was the dream scenario: 7 roughly Earth-sized planets, several in or near the Goldilocks zone, all around a single nearby red dwarf. A natural laboratory for testing our ideas about what makes a planet habitable and whether another truly Earth-like world might ever be within reach. So it's time to find out the truth. Once JWST turned its mirror toward TRAPPIST-1, what did those delicate starlight dips reveal about the actual atmospheres of these 7 worlds? Habitable zone versus actually habitable. The TRAPPIST-1 reality check. When we say a planet is in the habitable zone, what do we really mean? Because as JWST's data on TRAPPIST-1 come in, we are learning that in the Goldilocks zone and actually habitable can be very different things. The classical idea sounds simple. If a planet orbits its star at just the right distance, liquid water can exist on the surface. In the hunt for alien life, that became our first big filter. Find the right orbit, and you might find oceans. But while that works as a rough guide, it hides a brutal truth. This means nothing about whether the planet kept an atmosphere, blocked radiation, or had the right geology to recycle carbon and stabilize its climate. TRAPPIST-1 is our reality check. Here, we have 7 rocky Earth-sized planets, many in or near the habitable zone, around a relatively calm red dwarf. Optimistically speaking, this system should have been a jackpot, yet JWST's first detailed looks are sobering. For the inner planets, especially TRAPPIST-1b and 1c, Webb measured their thermal glow as they slipped behind the star. If they had thick atmospheres, those blankets of gas would trap heat and smooth out temperatures. Instead, they look almost bare, cooler on the night side, with no sign of a dense CO2 envelope, effectively airless, no realistic surface oceans, no surface life as we know it. TRAPPIST-1d, right at the inner edge of the habitable zone, is more mysterious. JWST has not seen obvious water vapor, carbon dioxide, or methane. It should be noted that this does not prove there is no atmosphere. A thick, cloudy sky or a deep global ocean could be hiding its fingerprints. But it reminds us that could host liquid water on paper is not the same as does host a stable, breathable atmosphere in reality. And over all of this hangs the star's history. Even though TRAPPIST-1 flares less than many red dwarfs, JWST and other observations tell us it has bathed these planets in high-energy radiation for billions of years. That radiation can strip atmospheres away, molecule by molecule. So if even this unusually quiet red dwarf is rough on its planets, how many truly Earth-like environments can we expect around the countless more violent ones? Kepler and TESS have shown us that small rocky planets are common. The galaxy is full of Earth-sized worlds. But while size is easy to count, JWST is now whispering a warning. Earth-like in radius does not mean Earth-like in environment. How many of those dots on our charts actually have thick, protective atmospheres and long-term, gentle climates? So let's begin asking a harsher question. Even if, somewhere within a few dozen light years, there really is a true Earth 2.0, blue oceans, clouds, and all, could we ever reach it with real spacecraft, real engines, and the limited energy of a single civilization, our data are early, and the universe doesn't care? So, before we rush ahead to interstellar engines and impossible journeys, we need to admit something uncomfortable. Our picture of these planets is still blurry. JWST has only just started to stare down the TRAPPIST-1 system, and the results are coming from the edge of what is even measurable. We are trying to read the atmosphere of a small, Earth-sized planet as it passes in front of a faint red dwarf 40 light-years away by watching the star's light dim by a few dozen parts per million. That is astronomy at the limit of sanity. It should be noted that every spectrum we show in the hunt for alien life is really a noisy, jagged line that has been cleaned, modeled, and interpreted. When we say no thick hydrogen envelope or no Venus-like CO2, what we really mean is that under certain assumptions about clouds, temperature, and chemistry, those options fit the data badly, change the assumptions, and the story can shift. This means today's confident headline can become tomorrow's quiet correction. So, let's begin by being honest about uncertainty. Future JWST campaigns might pull out clearer signals. TRAPPIST-1 could yet surprise us with hints of a balanced, Earth-like atmosphere. TRAPPIST-1G or some other outer planet could reveal unexpected water vapor or clouds that make a marginal world more habitable than we thought. And beyond TRAPPIST-1, new surveys may uncover an even closer, even more promising Goldilocks zone around a nearby star we have barely noticed. Optimistically speaking, the catalog of potentially habitable worlds is almost guaranteed to grow. Our models of climate on tidally locked planets will improve. Instruments after JWST may finally see biosignature gases directly. In the hunt for alien life, the details are very much in motion, but while the details can move, the background wall does not. The issues we are about to dive into, interstellar distances, energy requirements, radiation, travel times, do not care whether TRAPPIST-1e is a frozen desert, a water world, or a lush blue marble. They are baked into the physics of space itself. Proxima Centauri stays 4 light-years away. Accelerating a starship to a decent fraction of light speed still demands absurd amounts of energy. Cosmic rays still slice through metal and DNA, so it's time to find out the truth about what reachable really means. This video is not claiming that we already know there is no accessible Earth-like planet out there. Instead, we are asking a harsher, quieter question. Even if the universe is kind and nearby Earth 2.0s exist, what does it actually take to go from here to there? Hold two ideas at once as we continue. Our exoplanet map is evolving and may bring wonderful surprises. But the travel problem, the vastness, the cost, the danger, remains stubbornly, almost cruelly, fixed. And that is where we are heading next. Zooming out, how many nearby Earths do we really have? So if the travel problem is cruelly fixed, how many destinations are we really talking about? Is the galaxy overflowing with nearby Earths? Or are we living next to an almost empty cosmic parking lot? In the hunt for alien life, the raw numbers at first look incredibly generous. Kepler and similar missions have shown us that planets are common, not rare. When we zoom in on sun-like stars, a significant fraction seem to host at least one roughly Earth-sized planet in the Goldilocks zone where liquid water could exist. This means that across the Milky Way, there may be billions of potentially habitable, Earth-like worlds quietly orbiting their stars. But while the statistics sound comforting, the geography is not. Most of those systems Kepler sampled are hundreds or thousands of light years away. They are perfect for building graphs and probability curves, terrible for planning an actual mission. Kepler gave us a census of the distant city skyline, not a list of houses on our own street. So let's begin with that street. If we restrict ourselves to, say, 20 light years around the sun, the catalog shrinks dramatically. We have some intriguing candidates. Proxima Centauri b around the nearest red dwarf, the TRAPPIST-1 system at about 40 light years just beyond our 20 light year shell, and a scattering of super-Earths and mini-Neptunes around dim stars. It should be noted that none of these are confirmed true Earth twins. We do not yet have a planet with Earth's size, orbiting a sun-like star, with a directly measured Earth-like atmosphere and surface conditions, and the architectures themselves can be wildly different. TRAPPIST-1, for example, is so compact that all 7 of its planets orbit closer to their star than Mercury orbits our sun. Imagine compressing the entire inner solar system into a space smaller than Mercury's path, with every world tidally locked, one side in permanent day, the other in endless night. Our own system feels almost spacious by comparison, with Earth at a comfortable distance from a relatively calm star. Optimistically speaking, it is still quite plausible that within tens of light years, there is at least one world that is reasonably Earth-like, with a temperate climate and a protective atmosphere. Maybe there are even a few. But dozens of perfect blue copies waiting just around the corner? The current data do not support that fantasy, so it's time to find out the truth about the harder question. Even if we grant ourselves one solid target within 10 or 20 light years, what would it actually take to send something there? Not in 70,000 years like Voyager, but on a timescale a human civilization can care about. The answer forces us to push right up against the limits of physics, and then ask whether those limits push back. The tyranny of distance, why stars are so far away. So let's begin with the nearest real destination we could even dream of, Proxima Centauri. This star is just 424 light years away. That sounds almost friendly, like a next-door neighbor in our local cosmic suburb. But a light year is nearly 10 trillion kilometers. This means Proxima is more than 40 trillion kilometers from us. 40 trillion. The number is so large that our intuition simply gives up. In the hunt for alien life, we often talk about Proxima's planet and other Earth-like worlds, as if they are just waiting for us to visit. But while it feels close on a galaxy map, in real space, it is brutally far. Imagine driving a car at highway speed to the moon. Now stretch that trip out not for days, but for millions of years. That is the kind of scale we are dealing with when we talk about a single nearby star. To make this less abstract, we can return to our most distant explorer, Voyager 1. It should be noted that Voyager is not slow. It is racing through space at about 17 kilometers per second, far faster than any jet, fast enough to cross the entire United States in a few minutes. Yet at that speed, it would need over 70,000 years to reach Proxima Centauri. 70,000 years. That is longer than all of recorded human history. So what would count as fast enough on a timescale a civilization can care about? If we wanted to cross those 4.24 light years in a few decades, we would need at least 10% of the speed of light, around 30,000 kilometers per second. This means we are talking about moving a spacecraft roughly 1,000 times faster than Voyager 1, and still taking more than 40 years just to reach the closest star. Here is the pattern interrupt. It is tempting to say, fine, we just build better rockets. But the universe does not negotiate. Pushing even a tiny probe to 10% light speed runs straight into the rocket equation, which punishes you every time you try to add more fuel. The energy required climbs to absurd levels, and as you approach a significant fraction of light speed, relativistic effects start to matter, changing how momentum and energy scale. Optimistically speaking, we might one day manage that for gram scale or kilogram scale probes. But if accelerating something that small already looks extreme, what happens when we try to move an interstellar ship big enough to carry people, ecosystems, or even just the thick shielding needed to survive deep space for decades? The rocket equation versus our interstellar dreams. So if tiny probes already strain our imagination, what happens when we scale up? What does physics say when we ask for a real ship with people, air, and shielding, heading for an Earth-like planet light years away? To answer that, we have to meet the quiet villain of space travel, the Tsiolkovsky rocket equation. In simple terms, it tells us that to go faster, we must throw mass out the back as exhaust. but the more propellant we add, the heavier the ship becomes. This means we then need even more propellant to push that extra propellant, and so on. The relationship is exponential, not friendly. Doubling your target speed does not just double the fuel, it can multiply it into absurdity. Chemical rockets, the same basic technology that lifts satellites and Mars rovers, lose this game instantly at interstellar scales. Even if we filled a skyscraper-sized rocket almost entirely with propellant, the rocket equation tells us we would still crawl compared to light. In the hunt for alien life, that is a sobering realization. Our current launch technology is beautifully engineered, but fundamentally the wrong tool for crossing the gulf between stars. So we look to more powerful options. Nuclear fission, and especially fusion, promise exhaust velocities far beyond chemical flames. Concepts like Project Daedalus imagined a multi-stage fusion-powered craft, burning pellets of fuel for years, to reach perhaps 10 to 20% of the speed of light. Impressive, yes, but it should be noted that Daedalus needed tens of thousands of tons of fuel, and it still would have spent decades just accelerating before it could even coast toward a distant system in the Goldilocks zone. Energy is the other wall we hit. Accelerating a modest 1,000 kilogram spacecraft to just 10% light speed requires on the order of 10 over to 18 joules of kinetic energy. That is comparable to all the energy humanity uses in an entire year, and that figure assumes perfect efficiency. No waste heat, no losses, no structural mass, no atmosphere to climb out of. Real designs would demand far more. This is why projects like Breakthrough Starshot look so different. Instead of a huge rocket, they imagine gram-scale star chips, pushed by a vast array of Earth-based lasers, riding on photon pressure to about 20% of light speed. For something that weighs less than a paperclip, this is barely plausible if we build infrastructure on a planetary scale. But try to scale that to a crude vessel weighing thousands of tons, with a stable atmosphere and radiation shielding, and the required laser power and energy storage balloon into the realm of the absurd. So it's time to find out the truth. Even if we somehow pay this impossible energy bill, even if we beat the rocket equation with exotic propulsion, the universe has one more surprise waiting. At a fraction of light speed, space itself turns hostile, and every stray atom becomes a threat. Space fights back, radiation, dust, and centuries in the void. At high fractions of light speed, space stops being empty. It becomes an ocean of invisible bullets. Between the stars, the radiation never sleeps. High-energy cosmic rays, born in supernovae and black hole jets, slice through the void at nearly light speed. Solar and stellar particles stream out from every star, over a journey lasting decades or centuries. Each particle is a tiny roll of the dice against DNA, against nervous systems, against the delicate circuits that keep a ship alive. This means any truly interstellar vessel needs serious shielding, not just a thin metal hull. But while we can hide electronics behind thick slabs of water, metal, or magnetic fields, doing the same for thousands of people is a different story. Every extra ton of shielding multiplies the already absurd energy bill. It should be noted that cosmic rays are so penetrating that even meters of material only reduce, not remove, the threat. Over a lifetime in deep space, cancer, infertility, and neurological damage stop being rare risks and become background conditions. And then there is dust. At 10 to 20% of light speed, a grain of sand hits like an artillery shell, even a grain of smoke. A micron-sized speck carries the kinetic energy of a rifle shot. So, any starship racing toward an Earth-like planet cannot simply point its nose at the target and cruise. It needs a massive sacrificial shield at the front, perhaps a thick ice wall, or a constantly replenished cloud of gas and debris to vaporize incoming particles before they shred the main hull. In the hunt for alien life, we often imagine generation ships, vast world ships, where entire societies orbit a distant star only in their dreams. Thousands would live and die inside a rotating cylinder, never seeing a real sky, maintaining an artificial atmosphere and ecology for centuries. But can culture, politics, and mental health remain stable for that long? Can crops, microbes, and human genomes avoid slow degradation under radiation and isolation? Optimistically speaking, we have no data at all. Here is the pattern interrupt. What if the most realistic starfarers are not people at all? Robotic probes, stripped of fragile organs and emotions, can be wrapped in shielding, shut down for decades, and woken by a simple timer. Digital minds, if we ever create them, might tolerate the cold silence between stars far better than any biological crew. A probe carrying a few kilograms of electronics is far easier to accelerate than a flying city with a Goldilocks zone inside. So it's time to find out the truth about the Fermi paradox as well. Maybe the real question is not where is everybody, but why would anyone go anywhere when virtual worlds and rich local systems are so much cheaper than crossing the lethal dark between stars? If we can't reach another Earth, what do we do instead? If the real question is why anyone would leave, then where does that leave us? We have spent this whole journey chasing a dream, another blue planet, circling a distant star, with an atmosphere like ours and liquid water in a gentle Goldilocks zone. TRAPPIST-1 showed us something profound. Earth-sized planets are everywhere, but while they are common, truly Earth-like conditions may be rare, and the space between those worlds is unimaginably vast. Interstellar distances are not just big, they are brutal. Our fastest probes would need tens of thousands of years to reach even the nearest red dwarf. This means pushing a real crewed ship to a nearby system is not just an engineering challenge. It is an energy problem, a radiation problem, a how do you keep a society alive for centuries in a metal shell problem. In the hunt for alien life, we have accidentally discovered how hard it is for life to move at all, so it should be noted that we posed a binary question earlier. Are we a galaxy-spanning civilization or a solar system civilization with very long-range eyes? Optimistically speaking, physics is not actually forbidding interstellar travel forever, but while the equations allow it, the practical obstacles are so extreme that, for the foreseeable future, we are almost certainly a local civilization, not a Milky Way empire. Does that make the future smaller? Not necessarily. It just makes it different. If we cannot easily reach another Earth-like planet, we can build our own environments. Terraforming Mars, over centuries, into a world with rivers and a cold, thin, but breathable atmosphere, turning icy moons in the outer system into buried ocean refuges. Constructing O'Neill's cylinders, vast rotating habitats whose inner surfaces could host forests, seas, and city lights in permanent orbit around our own star. Beyond that, we might make distance itself less important. Rich virtual realities could let trillions of minds share experiences without ever leaving the solar system. World ships and digital explorers might drift slowly between stars, while most of humanity lives in light-speed networks wrapped around the sun. So, let's begin to see staying here in a different way. If this really is our island in the cosmos, then it is not a prison sentence, it is an opportunity. This means the stakes for protecting Earth, for keeping our biosphere stable and our civilization sustainable, are far higher than they first appeared. A damaged homeworld is not something we can simply replace, so it's time to find out the truth about ourselves. Knowing all this, would you still sign up for a one-way interstellar mission? Tell us in the comments. And if you want to help for real, support the telescopes, the probes, the planetary protection missions, because understanding our limits is the first step to making the very most of the universe we can actually reach.